AIoT is an exciting new area that combines AI concepts such as ML with IoT in order to facilitate a broad range of modern applications. Examples include biomedical smart wearable devices such as the Apple Watch, to Industry 4.0 applications, such as predictive maintenance of motors and pumps, wind turbines and smart grid renewable energy solutions. In all cases, these applications require analysis of real-time data from IoT sensors, such as ECG, current, temperature, pressure, gas, strain and accelerometers, in order to extract features of interest for classification with an ML model. However, in many cases we need to design and optimize filters with specialized characteristics and combine them with other filters and mathematical algorithmic operations, in order to extract wanted features and minimize any noise or unwanted features. As an example, consider the noisy wobbly sine wave shown here. This could be data from an accelerometer used in vibration analysis on a pump or motor in a predictive maintenance application. The wanted features are the sine wave's instantaneous amplitude and phase, which can then be further processed by extra mathematical algorithmic operations to produce an estimate of average amplitude and frequency. This can be then fed into an ML model to classify the intensity of the vibration and monitored as part of an asset maintenance program. Note that all other features, such as the low-frequency baseline wander and noise, are the unwanted features that we want to ignore. Also note that our simple predictive maintenance application can be improved with the help of extra filters and algorithmic operations, making it possible to obtain velocity and displacement data from the original acceleration data. Unfortunately, the challenge is complicated by the fact that many filter transfer functions that may be suitable for the application are defined symbolically, in either a textbook or academic publication. That is to say that they're somewhat exotic. As such, this requires strong knowledge of DSP and a symbolic scripting language to implement their specification. What we ideally need is a real-time experimentation environment, which has a powerful symbolic mathematical scripting language, and the ability to test filters out and modify their characteristics in real time on any streaming sensor data in a computationally safe simulation environment. In this video, we'll discuss the ASN Filter Designer's FilterScript live scripting language and IDE, and how it can be used for experimenting with exotic types of filter transfer functions for various AIoT applications with streaming data. ASN Filter Designer's FilterScript language and IDE is a feature-rich propriety scripting language developed by ASN, aimed at providing you with a safe environment for experimenting with the design and optimization of exotic symbolic filter transfer functions in real time, and then testing them out on captured or simulated datasets. The optimized filter can then be deployed to Matlab, Python or C# for use in an ML project or even to an ARM microcontroller for implementation in an AIoT application, in just a few clicks. The language uses a similar construct to existing technical computing languages, and builds upon the capabilities of the ASN Filter Designer's classical graphical filter designer, by providing over 82 design methods and scientific commands for filter design and mathematical operations. Our DSP experts have developed a number of filter design methods for both infinite and finite impulse response type filters, allowing you to get on with your experimentation rather than stressing over the details of the implementation. As seen here, with little or no programming knowledge, a second-order infinite impulse response notch filter transfer function, taken from a textbook or technical specification, can be defined symbolically by simply entering the numerator and denominator expressions in descending powers of z. Looks pretty easy, wouldn't you say? Let's now have a look at how we can define more symbolic variables and use them. Looking at our example more closely, we see that the transfer function requires omega c to be specified in radians per second rather than in hertz. If we prefer to work in hertz, it's easy enough to add a new symbolic variable to handle the conversion from hertz to radians like so. In order to set the gain of the filter at DC to 1, we need to divide the sum of the denominator coefficients by the sum of the numerator coefficients. This little scaling trick is due to the property of the Z transform, which is beyond the scope of this video, but suffice to say it can be used to set the gain of any infinite impulse response transfer function to unity or 0 dB at DC. Let's now have a look at the concept of interface variables. Where the environment truly excels is its ability to modify parameters on the fly, with the help of the so-called interface variables, allowing for real-time updates of the resulting frequency response. This has the advantage of allowing you to see how the coefficients of the symbolic transfer function expression affect the frequency response and the filter's time domain dynamic performance. As seen, an interface variable can be defined as an array of 4 values. Returning to our example, we would like to vary the R and FC symbolic variables in real time. Let's say that we wish to vary FC between 10 and 80 Hz, with a step size of 5, and set an initial value of 50 Hz. We can simply enter these values into the interface variable array as shown. Likewise for radius r, varying the radius between 0 and 1 with a 0.1 step size, we enter the following. Let's now put all of this together and have a look at the final script. We see the final code is split up into two sections around the main keyword. Executing the script just runs the upper section once, but the lower section is rerun when an interface variable is changed. It's as easy as that. Notice also the clear H1 keyword. As our symbolic filter is part of the filter cascade within the tool, referred to as the H2 filter, it is preceded by the H1 or primary filter, which is designed by the graphical filter designer. Therefore, if we wish to just use our symbolic H2 filter, we need to remove or disable the H1 filter from the cascade, otherwise the tool will augment the filters. If you wish to program the H1 filter directly from FilterScript, then the H1 num, H1 den and H1 gain keywords can be used. Let's now take this code and have a good look at the IDE. The ASN FilterScript IDE can be opened from the main UI. The IDE has been carefully designed as to not overwhelm the developer with options and provides all standard functionality found in other editors, including an IntelliSense for details on each command. A detailed reference guide is available via the Help menu, and I'd highly recommend visiting the Examples portal for detailed examples written by our DSP experts for a variety of AIoT applications, including various audio filters and filters for industrial and biomedical applications. Over 20 examples are also shipped with the tool, which can be found in the Examples directory. Certainly worth a good look. Let's now return to our example. If no session filter is available, the editor will load a skeleton script. Pasting our code into the editor, we can now begin evaluation. Notice that moving the mouse over the commands provides hints on the syntax. However, as we're not using any of the design methods in this example, the information will just be limited to interface variables and a few keywords. Running the script by pressing on the play button, we see that the output window produces a summary of the interface variables' current values and the results of the mathematical operations on each line of code. Notice that the frequency response and pole zero charts have also been updated. We're now ready to experiment with our expression. Once the script is running, we can open the interface variable controller and minimize the editor. The smaller interface variable controller makes it much easier to assess the filter's frequency response. But in this getting started video, I'm going to leave it open so that you can see how things are updated. Selecting FC and altering its value with the slider causes the transfer function to be automatically recalculated with the new variable value, while at the same time updating the charts in real time, allowing for an instant assessment of the new settings. As with the primary H1 filter designer, FilterScript is fully compatible with the signal analyzer, allowing you to assess filter performance in real time for a range of test signals. Launching the Signal Analyzer UI, and then opening the signal generator, we can define our excitation signal for our filter. Let's set up a DC signal with some 50 Hz sine wave interference, representative of power line interference, and some white noise. As our symbolic filter is a notch filter, we would like to cancel the 50 Hz sine wave and recover the DC component. The white noise can be minimized by combining our notch with an extra low-pass filter, but we won't cover that in this video. Moving the notch to 50 Hz, and adjusting the radius r, notice that we've cancelled the 50 Hz sinusoid completely. This now concludes this getting started video for ASN FilterScript. Check the description below for details on how to download the ASN Filter Designer and how to contact us if you have questions. Many thanks, and I look forward to seeing you next time.